Lecture 7.7, the interference intensity function. If a single light source is shined onto a screen, its intensity is, so I'm going to call this a single source intensity. I'm going to define this as I naught, and this is equal to the amplitude squared. So for the electric field, it's going to be the electric field squared. If two superimposed sources interfere and shine onto a screen, also the overlapping pattern's intensity is, so now we're going to have two interfering sources, which I'm going to define as IM. This guy is going to be equal to 2 times the electric field amplitude times our phase factor squared, and this becomes 4 I naught squared cosine squared of 1/2 V. So let's look at this thing picture-wise. We have the following. So the first thing I want to do here is that I'm going to draw a, I need to make sure I get my heights right. So let's say that I have this guy right here. So here's our line. So I'm going to have a single source. So let's say that the single source is going to be this high. And the reason why it's this high here is because it only depends on the amplitude squared. There's nothing special. So in this case, I look at this from here to here. This is I naught. And this is a single source. Now what I'm going to do is that I'm going to shine two sources that don't interfere. So now I'm going to look at two sources that do not interfere. So when I look at this one is then going to be twice as high. Right? That's shining two lights. Right? It's shining two lights onto the same screen but there's no interference. So I now have twice the light. So it should be twice as bright. Now the beauty of this whole thing is this guy. Now, if I have two sources that do interfere, what do we see? We see that they're able to move energy from dark to bright locations. And so when I'm looking at these intensities, what I'm seeing here is that this height is not twice as high, but 4 times as high in its maximal value. That's why we want interfering waves. We get a much bigger amplitude. So the intensity function goes by this here. So the intensity equation is usually written in the language of phase and path difference. So if I look at my phase and path, my phase, then this is 2 pi lambda times delta r. And then I know that my path difference is d sine theta. So if I put these all together, I can rewrite the phase as 1/2 phi. Then I'm going to get 1/2, and then I get 2 pi lambda times delta r, but delta r is d sine theta. And you could see here is that the reason why one would do this is that it simplifies because it gets rid of the factor of 2. So this guy is now written as pi d over lambda times sine of theta, and this is defined as the beta phase factor. And this is really a very, very convenient parameter. So this is the beta, and this guy is defined as the beta phase factor, because it's proportional to phi. So now if I do that, I can now go in and write the intensity equation. The intensity equation now reads, so I then going to have the intensity for 2 slits is then going to be 4 I naught squared cosine of beta, like this, but we don't write that. We don't typically calculate these things. Okay, so this is true for all values of beta, where beta is equal to pi d over lambda sine of theta. However, we typically calculate the relative intensity. And the relative intensity is cosine squared of beta with no 4 factor in there. Now, if I need the details of the intensity, then I have to put that 4 factor in there. So now what I want to do here is that let's just plot the intensity function. So by the way, I should have said this. Why is this the beauty? Because this normalizes the intensity function. If you do this, then we see here that cosine squared of beta when it's maximal will always be +1, or we could say that that's the 100% of the relative intensity. So let's sketch this out. So if I look at my pattern, I'll do the exact same thing as we did before. And so what I'm going to do here is that I'm going to draw my intensity pattern. So let's see here. So let's say that this guy has a shape like this. And then I'm just going to make combinations of these guys. So let me just copy and paste. So if I copy this, now I can just, oops, that's not what I want. If I copy this, then I'm going to have this guy. So now I'm going to copy these to be quicker, and then I'm going to just start pasting them in right here. So this is my first one right there. So now I can just start putting these guys in. And now let's go label these guys. So this is what I'm calling I relative. And this whole line up here, right, this line up here really tells me that this represents the maximal value. They all have the same intensity. So then we say that this is 100% of the intensity at this line. So what's best for us? Well, we still have the same process as before. We have MC. We have beta. Well, maybe I should be careful. Let's call this delta R. It still follows all the same process as before, but now we have the beta factor. The beta factor is the more powerful one. So let's look at this. So then this is MC equal to 0. And this will be +1, +2, +3, +4. -1, -2, -3, -4. I could write MD too. So if I look at the path difference, how's the path difference going to look? Well, if this is 0, then that means the next time I have a maximum, the next time I have a maximum, it has to be with the wavelength. They follow the MC value, just as we would have expected if we were just dealing with phi. But here's where the power here. It's the beta function that I like the best, because this tells me now it's pi, 2 pi, 3 pi, 4 pi, minus pi, and we have increments of pi. So beta is the most important one to actually look at. It's the simplest one. So now what I'm going to do here is that I want to look at some examples, and then we want to use an applet. Okay, so from lecture 7.6, we looked at two different cases of d over lambda equal to 1.5 and d over lambda equal to 3.0. So what I want to do here is that I want to insert, I want to copy that. So let me go copy this intensity pattern that we had, and then bring it into this sheet here. So this here is, I think I called this example 2. Now the reason why I'm doing example 2, just because it's 1.5. Then the next one is 3, which is a little bit higher. So now let's go look at this. Here's our intensity function right there. So when you look at the intensity function, what I can see here is that this represents theta, but I don't know any of the details of theta. But I do know the details of beta, right? Because for beta, what we know here is that this is 0. A maximum occurs at pi, and then the other maximum occurs at pi as well, positive pi. The minimas, look where the minimas are going to be. The minimas are going to be at minus pi over 2 plus pi over 2. And then over here, this has to be 3 pi over 2. And this is minus 3 pi over 2. So remember, these are not symmetric because the small angle doesn't apply anymore. So what I want to do here is that I want to calculate the beta phase factor and its relative intensity at theta equals to 30 degrees. Now, no, I don't know where 30 degrees is at. So the first thing that I got to do here is that I'm going to try to locate where 30 degrees is at. So let's go do that. So the first thing I'm going to do is that I need to calculate what the beta function is. So here we go. So now we want to calculate beta first. So if I calculate beta first, this is going to be beta, which will then be pi d over lambda times sine of theta. But we just said that we're using the previous one, which is 1.5, and we're setting theta equal to 30 degrees. Now you may remember, well, let's put this in. So here I'm going to get d over lambda is 1.5. And then I have the sine of 30, and then I have the pi. This is what's really important. Do not put pi into the calculator, because that's going to tell us where it's at. Now, the sine of 30 is a half, so a half of 1.5 is 0.75 pi. So this is beta right here. We now know what beta is. So the beauty of this is that I know its location. So if you look at the location, note that the minima occurs at half, so you know that that beta function has to be between this guy and there, so it's going to be somewhere in between pi over 2 and pi itself. So I'm going to say that it's going to be somewhere around right here. And what I'm saying, maybe I should do this in a different color here. This guy right here, I'm going to say is that guy right there is 0.7 pi. And then this location here is minus 0.7 pi. That's my guess. So it looks like it's right in between 0.5 and 1. Right? It looks like it's smack in the middle. So now that I have that, let's go calculate the relative intensity there. The relative intensity at 30 degrees, at theta equal to 30 degrees is then going to be this here. So then I've already calculated beta. So this is cosine squared of beta, but now I'm going to have cosine squared of 0.7 pi. Now here's where you got to be careful again. So here you must use radians in calculator. Or you have to convert that into degrees. So typically I have my calculator always in radians. So then if I compute this number, here's what I get. I get 0.50. Not a surprise because it's smack in the middle. It's going to then be the relative intensity at theta equal to 30 degrees. So now I know what that intensity is. So when I go back up here, this intensity at this spot is at 50%. Now what I want to do here is that I want to go in and I want to use the Fendt interference applet, and let's see how it compares for us. So we're going to use the Fendt interference applet. Okay, so let me go share my screen. Here we are. So what I've set here is that I've set the wavelength to 700 nanometers, excuse me, and the spacing is 1050. So when you look at that ratio, you're seeing here that that's a ratio of 1.5. So now what I'm going to do here is that I'm going to come in and I'm going to change this angle to 30 degrees. So look what it says here. If you look at this thing, you're seeing that at 30 degrees, it's in the middle between the peak and the minima, just like we calculated, and its intensity is 500. Excuse me, it's 50%. Exactly what we expected. Now, I just copied this. So now what I want to go here is that I want to come in and I want to show you what I have. So let me put this in right here. And if I look at this intensity here, let me make this a little bit bigger so it's easier to see here. Here's what you're seeing. From these two guys right here, you can see here that d over lambda, which is 1050 over 700, is exactly 1.5. And so you can see right here, I'm looking at this angle right here, 30 degrees, and look at the relative intensity. It's exactly what we just calculate it. Now, let's go look at our second example that we did before. And this is the one where we set, let's see, what we did here, we did example 2. So now we want to do example 1. And again, the order does not really matter. But what we did here is that we set D equal to, what was it? It was equal to 3 times lambda. So what I want to do here is that let's go look at that guy again. So let me go back and share my screen. And here's the applet. Okay, let me make sure I'm sharing the right screen. Yep, here it is. So what I'm going to do here is that I have to change this. So it's now a factor of 3, which is, it's 2100. And let's not pick an angle of, do I want to pick a different angle? You know what? I think I'm going to pick a different angle. Let's pick the angle 45 degrees. Okay, so I'm going to pick the angle 45 degrees. And this intensity is 0.862. So let's copy this and let's go calculate this thing. So here we're moving backwards. So in this example, we just did this. And I'm going to paste this guy in here. And just to keep that image nice and big, I'm going to spread it out. And so what we're seeing here is that we're seeing right here, we see that D over lambda is 2100 divided by 700 is exactly 3. And then what we want to do here is that I want to look at this here. So we're going to be looking at the angle of 45. And we need to calculate a relative intensity. And you can see here is that we're going to try to figure out its location. So let's go look at that here. So if I look at this thing here, here I go. So I got to do the exact same process as I did before. So let's go calculate beta. So then beta is equal to pi d lambda sine of theta. But now what we're doing here is that we're going to pick d over lambda to be 3, and then we have sine of 45. So if I plug this in, remember, I do not calculate pi. So this will be 3 times the sine of 45 times pi. And then let me get my calculator here. And I'm going to calculate this quantity. And I'm going to see here that that's going to be 3 times the sine of 45 gives us 2.12 pi, and this here is beta. So now what I want to do here is that instead of me creating that image, I'm just going to take their intensity profile and just use that. So let me grab this. So here's their intensity profile. And let's start labeling these. So if I put in beta here, what do we know about beta? Well, beta tells me that this has to be 0. The first one has to be pi. This one has to be 2 pi. And then this one is 3 pi here, all with signs. And then over here, I got pi, 2 pi. And then over here, I have 3 pi with my signs here. So if I look at my minimas, then this should be minus pi over 2, minus 3 pi over 2, and then this is minus 5 pi over 2. So if I look at this, let's look at this guy right here. This guy is at 2. So if I look at this, this is 2 pi. So when you look at this, I got 2.2 pi. Guess what? That looks to me that that guy is 2.12 pi right there. So now what we want to do here is that we want to calculate its intensity. So if I calculate its intensity, then I got to go into my calculator, and I could say here is that the relative intensity at theta equal to 45 degrees is then going to be the relative intensity. It's going to be cosine squared of beta, which will then be cosine squared of 2.12 pi. So remember, this has to be done in radians in your calculator. So now if I punch in that value, I get a value of let's see. The value you're going to get here is going to be 0.862 for the relative intensity at 45 degrees. And this intensity matches exactly what the applet is giving you.